Hello, this is the video on chapter 9. I hope you're doing well, and I hope you were able to watch the chapter 8 video. Let's just start. I'm gonna take my uh, video capture off there so we have more space. All right, so what is chapter 9 about? Well, let me give you a little summary of what we are going to do in this chapter, and then we go from there. Okay, so chapter 9 is about this idea that I'm going to explain in this problem. So we have here, it says a random survey of 75 death row inmates revealed that the mean length of time on death row is 17.4 years, with population standard deviation of 6.3 years. So what we have here is population standard deviation. So we have a population, and the standard deviation of this population is 6.3, right? All right. Now, you were conducting a hypothesis test to determine if the population mean time on death row could likely be 15 years claimed by a study. So there is a study, somebody has claimed that the mu of the population, which is of course unknown, they claim that that mu is 15. So we are going to do a counterclaim, which is basically a logical complement of that. So if that says mu is 15, we're going to say mu is not 15. And later we're going to talk about this, but we're going to call this null hypothesis, represented by h sub 0, h naught. And the other one is the alternative hypothesis, and we're going to represent it by h sub a. So we're going to talk about these. Don't worry about those names yet. So somebody claimed that mu of the population is 15. So how do we test this? So in this chapter, we're going to go through a procedure to test that claim. It's called hypothesis test. So we're going to take a sample, and they did that. So the sample size is 75. And they calculated x bar, and they figured x bar is 17.4. Okay? Now, here's the question. So we were going to test that whether mu is 15 or not. So the way we do it is we take a sample and we see if we have evidence against this claim, right? So do we have evidence against it? Well, our sample says that the mean is 17.4. Their claim says the mean is 15. Obviously they're different, but is that different enough for us to reject the claim that mu is 15? That's the idea in this chapter. How do we know that is different enough? So what do we mean by that? All of that we're going to talk about in this chapter. So the way it works is this. We're going to say, okay, we assume that you're right. The mu is 15, okay? That means we assume that this hypothesis here, null hypothesis, that's what it's called, is true. So if that is true, then if we were to take samples of the same size, and many of them, and calculate different x bars, what is the probability that we are going to end up with a number that big, right? Well, let's see. We know from previous chapters that x bars make a distribution, and that distribution of x bars is normal, with the mu of the x bar is the same as the mu that is claimed, which is 15, and the standard deviation of the x bars is, well, we know from previous chapter again, is 6.3 divided by what? Square root of 75, which when you put in the calculator, you're going to get about 0.7. Well, let's put it in a calculator and see. So we're going to get 6.3 divided by square root of 75, which is let's say is so we're going to say is 0.727. Okay, that's the point right there. All right, so now the question is, okay, so we know the standard deviation and we know the mean of that distribution. So what is the probability that we're going to end up with what? End up with a number like that. Now, they claim that mu is 15. So the evidence against that could be coming from the right-hand side, or it could come from left-hand side, right? So if we get a number that is much smaller than 15, that also refutes this, right? If we get a number that is much bigger than 15, it also refutes that. So what we're going to do is this. We're going to say, okay, what is the probability that we're going to get a number up here, right there, that is that far, right? That far away from 15. How far? That far. Well, how far is that? Well, let's see. We can find the z-value. What is the z-value for 17.4 minus 15? That's how far from 15 it is, 17.4. But how many standard deviations is that? Well, I don't mean this is standard deviation. I mean this one, right? Which is 0.727. And that number, if you put in a calculator, is going to be, well, let's see. Well, where is my calculator? That number is 17.4 minus 15 divided by 0.727. That is 3.3. That means how many standard deviation? About 3.3 standard deviation, right? Now, so this is z, and we know z's are actually a standard normal distribution. So if you convert these x bars to z's, then the mean goes to 0, and the 17 point something goes to 3.30. Now, under a standard normal distribution, what's the probability that we're going to get a number that far away to the right and also that far away to the left? Because remember, we could also get a number that what? That is much smaller than 15 and refute this claim. Now, how much area is to the right of 3.3 and to the left of negative 3.3? That number is called the p-value, and we're going to talk about that. Now, if that number is really small, we are going to what? We are going to refute this null hypothesis. Now, is that number small? Yes. How do we find how much area is that? Well, we have to find out how much area is to the right of 3.3 under standard normal distribution, which you learned in chapter 6. normal CDF, and then we're going to go from 3.3 comma 10 to 99 comma 0 comma 1, which is very small number, but that's just this area. Now we know that this area is exactly the same. You just multiply it by 2. So we're going to multiply that by 2. We're going to get a really small number. That number is e to negative 4, means I have to move the decimal place to the left 4 places. So let's do it over here. So we got 9.6696. I'll move it 1, 2, 3, 4. Right? So this number is really small. It's like, even if you move the decimal 2 places to the right, make it percent, it's like less than 0.1%. It's really a small number. That means now we have an argument. Our argument is going to be, well, since this number is really small, it's like 0.0009, then we argue that we are going to refute this claim. Why? Because given, if we assume that the mu is 15, then if we were to take sample of size 75 and find a mean, the probability that we would get a number this big, that far, to the right or to the left of 15 is only what? That. So that means there is 99.99999% chance that actually we would get a number different than the number that we got. So then our conclusion is that we are going to reject the null hypothesis. So we say that we have enough evidence to reject it. Okay, so that's the process of that is called hypothesis testing. Now let's go over this. So what we want to do is this. First of all, we want to learn how to write hypotheses for a problem and what do they actually mean. Then we're going to talk about what kind of distribution do we use here to talk about how far away the numbers are. And then we're going to talk about what types of errors are involved here. Can we make mistake? Yes, we can make mistake. So how far, what's the probability that we're going to make mistakes? We're going to do all that. We're going to do all that in this chapter. Okay? So let me erase all that and start the chapter. So this chapter is about hypothesis testing with one sample. And so here are what we're going to learn in this chapter. Differentiate between type 1 and type 2 errors. Describe hypothesis testing in general and in practice. Conduct and interpret hypothesis tests for a single population mean. And whether the standard deviation is known or the standard deviation of the population is not known. And then we're going to talk about how to do it for proportion. So let's start. So what are those hypotheses? Well, we have the null hypothesis, which is a statement about the population mean or proportion. In this chapter, we only talk about mean and proportion, but we could also talk about other parameters. These are the two parameters we're going to talk about in this chapter. Okay? So null hypothesis is a statement about that. This statement either says basically mu equals to a number, right? Or it says proportion equals to a number, or something similar to that, maybe less than or equal to or greater than or equal to. But we're going to see that. Now, alternative hypothesis is a claim, it's a different claim, right? And that's against that claim. Whatever that is, this one says the logical opposite of that. Logical opposite of that is not that. Logical opposite of this is greater than. Logical opposite of this is that. So if the null hypothesis says equal to, the alternative hypothesis says not equal to. If the null hypothesis says less than or equal, the alternative says greater than. If the null hypothesis says greater than or equal to, then alternative hypothesis says less than. We always have equal sign in null hypothesis in this one because we need that. Why? Because we always have to assume that the mean is equal to a number or proportion is equal to a number. Otherwise, we are not going to be able to use the central limit theorem and talk about, distribution of x bar and all that, x bars and all that. Okay, so null and alternative hypothesis, we talked about that. We always put equal sign in null hypothesis, and then the other, the alternative is under alternative hypothesis. All right, so some researchers, many researchers actually, they just use equal sign in any case for null hypothesis because that's what we assume. But the alternative hypothesis depends on how the claim is made, right? So, all right, so if the claim says that they believe that this is less than or equal to, well, then the alternative would be greater than. If the claim says equal to, alternative is not equal to. If the claim, when I say the claim, I mean the claim that is in null hypothesis. Both of those are claims, but one of them is claimed by somebody, right? So if the null hypothesis says greater than or equal to, the alternative says less than. All right. So here is how do we write the hypotheses for this? In a population of fish, approximately 42% are female. A test is conducted to see if, in fact, the proportion is less. So you see, they're trying to see if the proportion is less. So that means that's the alternative hypothesis. And it's about proportion less than 0.42. And the null hypothesis is going to be what? Greater than or equal to 0.42, like that. Okay? The American family has an average of 2 children. What is the random variable? Describe in words. Well, the random variable here is just the number of children that families have. So the variable here, it's is number of children an American family has. And the parameter here is the average number of children an American family has. Now, if that were a claim that this is the average equals to 2, that's how we would write it. And that would be the alternative. Now again, both of these are claim, right? So this is a claim and this is a claim, but one of them is the one that we care about because we want to know whether we support it or reject it, right? So for example, this could be the claim. If that's the claim, then we're going to try, we always either reject the null hypothesis or fail to reject it. If we reject the null hypothesis, then we are supporting that. If we fail to reject the null hypothesis, then we are supporting whatever is here, right? And we're going to talk about this a little bit more later. All right, random survey of 75 death row inmates revealed that the mean length of time on death row is 17.4 with a standard deviation of 6.3. That's the one we did at the first thing we did, right? If you were conducting a hypothesis test to determine if the population mean time could likely be 15 years, What would be the null hypothesis and alternative? Well, those would be the ones, right? Why? Because it says here, if you're conducting a hypothesis to determine if the population mean time on death row could likely be 15. So that means this is what you're testing. So a medical trial is conducted to test whether or not a new medicine reduces cholesterol by 25%. State the null and alternative. Again, the null hypothesis says that proportion equals to 0.25. The alternative says is not equal to. We want to test whether the mean height of 8th graders is 66 inches. State the null and alternative. Well, again, we want to test whether the mean height of 8th grader is 66. So that's equal to. Equal to goes here, not equal to goes there. Always the one with equal to goes in null hypothesis. We want to test if it takes fewer than 45 minutes to teach a lesson plan. State the null and alternative hypothesis. Well, let's, it's too quiet here. Let's put some music in the background. There you go. So, so let's go back to the discussion. So we want to test if it takes fewer than 45 minutes to teach a lesson plan. State the null and alternative hypothesis. Well, we want to know if it takes fewer than 45 minutes. So that is less than. So you see that goes here because there is no equality there. So we have to put it there. And then here goes the logical opposite of it. Or logical complement, if you want to say. On a state driver's test, about 40% pass the test on the first try. We want to test if more than 40% pass on the first try. So we want to test that. That means greater than. So it goes there. Some of the following statements refer to the null hypothesis, some to the alternative. State the null and alternative hypothesis in terms of the appropriate parameter, mu or p. The mean number of years Americans work before retirement is 34. Well, that's mu, right? At most, 60% of Americans vote in presidential election. At most, that means less than or equal to. And it's proportion. The mean starting salary for San Jose State University graduates is at least $100,000 per year. At least means greater than or equal to. And is mu. 29% of high school seniors get drunk each month. Well, that is proportion and is equal to. And fewer than 5% of adults ride the bus to work in Los Angeles. Fewer than 5% means less than 5%. All right, I'm going to let you read this yourself and do them. I'm just going to move on. All right, so outcomes and the type 1 and type 2 error. Well, the hypothesis, the null hypothesis, remember we always assume the null hypothesis is true. Now, of course, in reality, actually, it could be true, or it could be false. But we always assume it's true, but it could be false. What if it's true? What if H null is true, and we reject it, right? We reject a true null hypothesis, then that is an error, right? And it's called the type 1 error. So type 1 error is when you reject something that is true. Now, what if it's false? Well, if it's false, then if we do not reject it, then that's an error. And that's type 2 error, right? If something is not true, it's false, and then we fail to reject it, that is type 2 error. Now, otherwise, that's a correct decision. If it's true and we don't reject it, that's good, right? If it is false and we reject it, that's true. That's a correct decision. So there are 4 different outcomes, right? And 2 of them are errors and 2 of them are correct decisions. All right. So here is an example. Frank's rock climbing equipment is safe. So suppose that H null says that Frank's rock climbing equipment is safe. What if it's true and Frank's rejects it? Well, that's type 1 error, right? So that means these are good equipment, but he refuses to use them and he thinks that there's something wrong with them. All right? Now, what if they're not safe and then Frank fails to reject them? Well, that would be type 2 error, right? Which one is more serious? Well, think about it. If he rejects some safe equipment, at most he's going to go buy some more, or he's not going to take him to, climbing, rock climbing. There is no danger in that. He just maybe wastes some money. But if he thinks that they're safe, but actually they're not, and he refused to, fail to reject them, that means it doesn't reject that they're actually not safe. Then rejects that they're, so fails to reject that they're safe, then that would be type 2 error, which is a serious error because he would take the equipment with him and he might actually fall, right? All right, so type 1 error and type 2 error. Now type 2 error, type 2 error we don't calculate in this course, but type 1 error we don't calculate that either, but we are given that. So remember we said, the first example I said that it's possible that we get a number that big, right? 17 something, remember that? Well, under a normal distribution, we can say there is actually 5% chance that we're gonna make a mistake. Remember, 95% of the data is between negative 1.96 and 1.96. Remember that from chapter 8? So that means if we consider this area to the right of 1.96 and to the left of negative 1.96, that area is called alpha, which is 5%. Now, alpha is another name for type 1 error, because if a number falls in the tails, remember, we're going to say, oh, we're going to reject that idea that mu equals to a number, because by chance you only have 5% chance to get a number that big. So we're going to reject it. So that alpha right here is basically the area in the tails, and that is predetermined. Depends on level of significance that you choose. Just like in chapter 8 we had confidence level. Now in chapter 8 we care about what's in between, but in chapter 9 we care about what is in the tails or in one tail. Sometimes we only have one tail. So the area in the tails is named alpha, and that means type 1 error, because it's basically the probability of rejecting the null hypothesis. That's what type 1 error is. So if a number falls here, we reject the null hypothesis. So that is the probability of rejecting a null hypothesis. And we accept that and we start with that. So that is given. All right. We're going to talk more about that later. So I'm going to go to another one. A certain experimental drug claims a cure rate of at least 75% for males with prostate cancer. describe both type 1 and type 2 errors in context, which error is more serious? Well, type 1 error would be that this drug actually is good and this patient rejects it. That means the patient says, no, I don't want to take it, I don't believe you, right? That's type 1 error. So what does the patient do? Well, the patient might go get some different drug or different procedure instead of this one. May actually work for him or may not work for him, but not direct 100% danger. There is no direct results that is dangerous because of this decision. It just might not use this method, might go to some other method. Now, to deal with the cancer. Now, what about type 2 error? Type 2 error is when this drug actually is not good, but the patient thinks it's good and uses it. What happens? Well, that's the sure danger. Why? Because this patient has cancer and we know for sure that this drug is not going to work. This is not true. Then what happens? For sure, the patient is not going to cure the cancer because it's relying on this drug that is not good. Okay? So that's type 1 and type 2, and in this case, type 2 error is more serious, right? All right, state type 1 and type 2 error. I'll let you do this. I'm gonna move on. All right, so again, this is the big picture. I talked about that with that first example. We have a population, right? And somebody claims something about this parameter of this population. In this case, let's say mu. And then how do we test it? We take samples and then find X bar, which is a point estimate for the population parameter. And then we assume that these X bars make a normal distribution with the mu the same as the mu in the population. Now this mu sub 0 means the mu that is claimed in the null hypothesis. So that's what that means. So now, so what we're going to do is this. We're going to take this number, X bar that we get here, then we're going to do this to it. This is Z, of course, in this case. It's going to be a normal distribution. So we're going to take X bar and then convert it to a Z score. That Z score is called the test stat. Test stat. So the test stat is the statistic we get from the sample, and we just find the Z score for it. And that is called the test stat. Now that test stat, we're going to put it in the Z distribution and see where it falls, right? And if it falls here, then we're going to find this number as well and find the area in the tail, and that would be p-value. That's what we call p-value. Now, we're going to talk more about this, but for now, that's what that is. All right, now, what if we don't do that? Instead, we're going to do this. I'm going to erase all that. So instead, this is what we're going to do. We're going to say, okay, how much error are we going to accept? So let's say we accept that 5% is in the tails. That means we accept that it's possible for us to make a mistake 5% of the time. That means it's true that the null hypothesis is true, mu is whatever they claimed. We took a sample, we find X bar, and for us to reject that, there is 5% chance, because if you take this number and this number falls in the tails, then we reject it. We reject the null hypothesis. Now, what do I mean by falling in the tails? Well, I mean that let's say alpha is 5%. If alpha is 5%, then we know these numbers are negative 1.96 and that one is 1.96, right? So what happens is that when we get this z, if that z is to the left of negative 1.96 or to the right of positive 1.96, then we're going to go back and say, wait a minute, we don't believe in that. This, whatever you claim, we reject it. Why? Because there is only 5% chance that we're going to get a number that far away from the mean. And we did. So we reject it. So as you see, there are two ways to do that, right? One way is to just take a z normal distribution and take this number, wherever it falls, find the area to the right of it, and also to the area to the left of whatever that number is, negative of it, right? And this area is called p-value. Now, or we can set up our alpha here and then take this number and see where it falls. If it falls in the shaded region, then we reject. So this region is called rejection region based on alpha that is given. So we can set up rejection region and then find this number and see where it falls, right? Or we can just directly take this number under a z distribution and see how much area is to the right of it and how much area to the left of a negative of that number, and then use that p-value. The way we reject is that if p-value is smaller than alpha, we reject. That means if this area is smaller than this blue area, we reject. And that makes sense because how can that happen? That happens if this number falls inside here, and you see if I find area to the right of that number and to the left of this negative of that number, you see the red area is smaller than the blue area. See that? So that means that the p-value is smaller than alpha, and then we reject. Again, we're going to do many examples of this. That's a big picture, so we know where we are going with this. Now, remember we said that this is not the only way to write the null hypothesis. Somebody might say, well, look, I think mu is less than or equal to some number. Then the alternative would be what? Then the alternative would be that mu is greater than some number. Now, so if somebody claims something like this, you're not going to go look for numbers over here to reject it. You're not going to, I put it in the wrong side. Let me erase that. Oops. So you're not going to go look for numbers over here to reject this, because if you find a number here, that doesn't provide evidence to reject this, because they already said that mu is less than some number. And if you find a small number, you can't really say anything against it. But if you find a number on this side, right? So we don't care about this side because that side doesn't provide any information that we can use. It is this side that is going to provide information that we can reject this. But the question is, let's say they say this is 15 and you find 17. Is 17 bigger than 15? Yes, but how big? Is it big enough for us to reject? Well, that's the idea we're going to talk about here. But if the H naught or null hypothesis is less than or equal to, then the alternative hypothesis is greater than, and that tells us where we should look for numbers. So if that's the case, then we have a right tail test. That means we're looking for numbers on the right tail. We don't care about the left one, because the left tail doesn't provide anything. And if the null hypothesis is mu greater than or equal to some number, then the alternative would be mu is less than that number, that means now we're going to go to the left tail and look for numbers here that we can refute that, right? Because they say mu is greater than or equal to some number. If I go over here and find a big number, so what? They already said that. So basically here is where we're going to end up finding evidence against it. So depending on what is in the alternative hypothesis, so alternative hypothesis says mu greater than some number, we have a right tail test. If the alternative hypothesis says mu is less than some number, then we have a left tail test. And if alternative hypothesis says mu not equal to some number, then we have a two-tailed test, well, which is right there, two-tailed test. Okay? Again, we're going to talk about this more details later. All right, now the same thing happens in chapter 9 that happened in chapter 8. What is that? That when we don't know the sigma of the population, the distribution of x bars is not going to be normal. And when you convert it to scores, in this case would be t-scores from chapter 8, remember? These t's make a distribution that is not normal, is of course t-distribution with degrees of freedom of n-1. So again, the same thing happens. We either have two-tailed test, left-tailed test, or right-tailed test, but the calculations are done not using normal distribution, but t-distribution with n-1 degrees of freedom. And that happens if we don't know the standard deviation of the population. Okay? And next is proportion. So if what is claimed is, if the claim is about proportion, then we take a sample and we find p prime, and we know by, again, from chapter 8 that p primes are normally distributed with the mean the same as p of the population and the standard deviation of that right there. We know that from chapter 8. So if somebody claims something about a proportion, the proportion equals to a number, then what we're going to do, we're going to take a sample, find p prime, convert it to z, and then go over here and see where that number falls, right? So again, what I just gave you was a big picture of 3 different things we're going to do in this chapter. Let me go back and do it again, just mention it. You see, that's where the standard deviation of the population is known. Take a sample, find x bar, convert it to t-test, take t-test over here and see where it falls. If the standard deviation of the population is unknown, then you take a sample, find x bar and s, because we need it over here, and then convert it to t, take t and bring it over here and see where it falls. That's what we're going to do. And if the proportion is the parameter, you take a sample, find p prime, convert it to t-test, to test that, and for proportion is always normal, and it would be normally distributed. We take that z, bring it here, and see where it falls. We either find p-value or we do with rejection region. And again, we're going to do a few of these later. All right, so some assumptions here we make. The population doesn't matter what form it has if your sample size is greater than or equal to 30. So it doesn't matter if the sample size is greater than 30, greater than or equal to 30, then it doesn't really matter what the original population looks like. Then if we know sigma, we use normal. If we don't know sigma, we use t. That's the rule. So again, if the sample size is greater than or equal to 30, it doesn't matter what the original population looks like. But if the sample size is less than 30, then the original population has to be approximately normally distributed for us to be able to use this method. So again, we do the same thing. If sigma is known, we use n. Sigma is not known, we use t. Okay? But the only difference is that assumption that we usually make. So you're not going to find any examples here that this is not true. So don't worry about that much. All right, a population has a mean of 25 and a standard deviation of 5. The sample mean is 24 and the sample size is 108. What distribution should you use to perform a hypothesis test? Now, first of all, do we know the standard deviation of the population? Yes, here you go. The standard deviation is 5, right? So population has a mean of 25 and standard deviation of that. The sample mean is 24 and the sample size is 108. Now, there is no claim here. We're not told to do this. But if we were to set this up, if somebody claims that mu, let's say, equals to 25, right? If somebody claims that, then the alternative would be that mu is not 25. And we take a sample of what size? There is a population. Do we know sigma? Yes, it's 5. So mu is claimed to be 25. So we take a sample, and then what's the sample size? The sample mean is 24 and sample size is 108. So 108 and x bar is 24. You see? Now we can easily do the testing. So we can take that 24 and convert it to z. That would be 24 minus 25 divided by what? 5 divided by square root of 108. Oops. I erased everything by mistake, but that's okay. So that's 108 and the x bar was 24. This is claimed to be 25. So what do? We take 24 and subtract 25, divide by standard deviation of the population, which was 5, divided by square root of 108. This would be our z. And because we said that the alternative hypothesis is actually not equal to, this is a two-tailed test. So there are two ways to do it. First of all, we are not given alpha. If we are not given alpha, we assume it's 5%. So we can put alpha, we can do rejection region, right? So we're going to put negative 1.96 here and 1.96. This is our tails. And then we're going to get this number and see where it falls. Let's see where it falls. Well, we have to calculate that number. What's that number? Well, let's say 24 minus 25 obviously is negative 1. I'm going to divide it by, not by 5, but 5 divided by square root of 108, which is negative 2.07, right? Now, negative 2.07, let me get a, so this is negative 2.07. This number falls inside the tail here, right? So if we were to do this test, we would reject that. At what? At 5% level of significance. So that means we accept we could be wrong 5% of the time. And we say, based on that, we reject because we have data to support it. You see, in real life, I think we talked about this before, in real life, if you hit the jackpot, you say, wow, I got lucky. But in the statistics, if you hit the jackpot, we say, wait a minute, something is wrong. You go back and say, no, we're going to reject that. Because what just happened is a rare event. It's something that was not supposed to happen easily, but it did. So we go back and reject this. Make sense? All right, so we didn't have to do this. I just did it to see the structure of what we're going to do in this chapter. All right, so now, what if we were doing it with the p-value? Well, then we would put this over here. I mean, not there, but over here, right? So that would be negative 2.07. And also we put over here 2.07. Then we would find the area here. Well, we can find this area and multiply it by 2, right? So let's do that. So how do I find that area? Well, that would be normal CDF from negative infinity, right, to negative 2.07 and 0 and 1 there, which is 0.01, let's say 0.02. That's 2%, but I mean, we have to multiply it by 2, right? Because there is another area on the other side, right? We didn't count that. So that means it's about 0.04, 4%. Now, 4% is smaller than 5%, so we reject. So 4% would be our p-value, which is the probability to get a number this far or even further than that from the mean. And that probability is about 4%. But remember, we accepted 5% probability, and that is smaller than what we accepted, so is within our range, so we say yes, we reject it. Okay? All right, now if this number was something like, let's say 0.5, then it would end up over here, and that would indicate that we did not have enough evidence to reject this. All right, so let's move on. Which distribution do you use when? So here, of course, the answer was normal. Why? Because we know the standard deviation of the population. Which distribution do you use when the standard deviation is not known and you're testing one population mean? Assume size is large. Well, we use t-distribution, right? Why? Because the standard deviation of the population is not known. All right. So if you're testing a single population proportion, so if the population, we're talking about p in the population, we know p is x over n. So basically x is going to be binomial, just like chapter 8. X is binomial, and if you divide it by n, then basically you have to divide the mean of binomial and the standard deviation of binomial by n when you take a sample, and that would give us the mean and the standard deviation of the p primes, and we talked about that in chapter 8, so we're going to use it again here. So if the population parameter is p, we take samples of size n, we find p prime, then we're going to use z to decide. So for proportion, we use z. Okay, and I'm going to let you read that already, so I'm going to move on. You're performing a hypothesis test of a single population proportion. What must be true about the quantities of NP and NQ? Well, just like chapter 8, NP and NQ should be greater than or equal to, greater than 5 in order for normal approximation to binomial to work, right? To be close enough. So it has to be greater than 5. You're performing a hypothesis test of a single population proportion. The data come from which distribution? Well, binomial. X has to be binomial. It is believed that Lake Tahoe Community College algebra students get less than 7 hours of sleep per night on average. A survey of 22 generated a mean of 7.24 and with a standard deviation of that. At a level of significance of 5%, do the algebra students get less than 7 hours of sleep per night on average? The distribution to be used for this test is what? So here we have a population. Do we know the standard deviation of the population? Well, let's see. No, we are not given that. So we don't know the standard deviation of the population. And we know the claim is that a survey of 22 generated mean of that standard deviation at a level of significance of 5%, that is less than 7. So here we go. So that means here the alternative hypothesis is that mu is less than 7, so this would be greater than or equal to 7. Okay, now, so this is a left tail test because of that. And what kind of distribution? Well, we don't know sigma, so we're going to have to use t with degrees of freedom of, what is the sample size? 22 minus 1. So that's the distribution we're going to use. And what do we do? Well, we take a sample of size 22 and calculated x, they did actually, calculated x bar is 7.24. Now we're going to take that 7.24 and turn it into t and bring it over here and see where it falls. So that's the question, wasn't to do it here. The question was what type of distribution you have to use. We're going to have to use what? Answer is D. It would be a t distribution with 21 degrees of freedom. All right, so let's look at some more example. So it says, suppose a baker claims that his bread height is more than 15 on average. Several of his customers do not believe him. So to persuade his customers that he's right, the baker decides to do a hypothesis test. He bakes 10 loaves of bread. So basically he takes a sample of 10 of his own breads, right? And then the claim is that the height is actually greater than 15 centimeters. So that's the null hypothesis, and then we can do a test, right? So the standard deviation for the height of all the breads he has ever made, according to him, is 0.5. So the population has a standard deviation of 0.5, right? And here's the claim. So we're going to take a sample of size 10, right? N is 10, and we're going to find x bar. And he did. And let's see what he got. He got 17. So this is a right tail test. So we're going to take this 17, convert it to z, because we know what? We know standard deviation of the population. And then bring the z over here as a right tail. And then either do p-value or use alpha. We're not given that yet, so let's see. So the mean height of the sample loaves is 17. The standard deviation for the heights is 0.5. So now we can do this test easily. So let's do it together. So this is a right tail test. So we can do it two different ways. We can use the 17 here in x bars distribution, and we know this is 15, and we know the standard deviation of the x bars is the standard deviation of the population divided by square root of 10. So basically how much area is here is the p-value. What is that? Let's see. Well, that is, let's see. We have to go again to normal CDF and 217 comma 10 to 99, comma, now, so 17 to 1099 to 10 to 99, that area. The mean is 15, so we'll put 15 here. And the standard deviation is 0.5 divided by square root of 10. That is a really small number. Look at that, that's 10 to negative 37. So it's almost practically zero. What does that mean? It means that the probability to get a number that big, assuming that the mean is 15 and standard deviation is that, is almost zero. That means this event that it just happened had a almost 0% probability, but it occurred. So what do we say? Well, we say that we don't agree with the assumption. And the assumption was that mu is less than or equal to 15. So we're going to reject that and support the Baker's claim. Now, what if you convert it to z? Well, if you want to convert it to z and use z distribution, then you're going to have to convert that to z. 17 minus 15 divided by that standard deviation, 0.5 is 0.5 divided by square root of 10. So what is that? Well, let's see. 17 minus 15 is 2 divided by 0.5 divided by square root of 10. That's 12.64. So that number is 12.64. And we don't even have to use the normal distribution, the standard normal, to see how much area is here. It's almost zero. Why is almost zero? Is because, get rid of that, because we know that most of the normal distribution, a standard normal distribution, is between maybe -4 and 4. There is very little amount after 4, but this is 12.64. So the probability that z is that big to the right is 0, right? So that is using p-value. Now, if you were to use rejection region, you would set up a distribution for z, and you would say, okay, what's the number here that has, let's say, 5% to the right of it, right? What's the number that has 5% to the right of it? That would be 1.645, right? Why? Because you know from chapter 8 to how to find these areas in the tails. So now if we convert that 17, remember, to z, we got like 12 point something. 12 point something is way over here, so it's inside the rejection region. Because it falls in the rejection region that we set up based on alpha equals to 5%, then we reject that. Okay. All right. So in either way, we can reject that. All right. There is a video clip I want you to watch, and there is a problem from the video clip that I have here. You need to watch the video in order to understand that problem. But watch the video and look at that problem. So watch the video and then look at that problem. All right, so using the sample to test the null hypothesis, use the sample data to calculate the actual probability of getting the test result called the p-value. So this is the idea of p-value I just described. The p-value is the probability that if the null hypothesis is true, the results from another randomly selected sample will be as extreme or more extreme as the results obtained from the given sample. Is a little maybe vague at first, but is really not that hard. So here's the population. Suppose mu is supposed to be equal to some number. So let's see. Mu is supposed to be to some number. And then you take a sample, and suppose that our hypotheses are given by, some number and then not equal to some number, right? Not equal to some number. So mu not equal to some number, and mu equals to this number. Okay? Now, you take a sample of size n, and then you find x bar, then you convert x bar to z. What do you do with it? Well, you're going to put that z over here, and also you find the negative of that number and you put it over here, and you find this area. That's our p-value. So now you see what it means. It says p-value is the probability that if the null hypothesis is true, if we accept that this is mu, we accept this, we assume that it's true. If we do that, then p is the probability, p-value is the probability that the results from another randomly selected sample will be as extreme or more extreme as the result obtained from the given sample. So if we were to take another sample, what's the probability that the x bar that we find ends up being this far or even further from the mean? And that's the p-value, right? That's the idea. All right, so think about that. Maybe you can rewind and listen to that one more time. But that's the idea of p-value. So a normal distribution has a standard deviation of 1. We want to verify a claim that the mean is greater than 12. Sample of 36 is taken with a sample mean of 12.5. What is the p-value? Well, again, we have to see what's going on here. Normal distribution has a standard deviation of 1. So the standard deviation is given, right? So that's the standard deviation is 1. Now, we want to verify a claim that the mean is greater than 12. So that means the null hypothesis, the alternative hypothesis is that the mean is greater than 12. So that means the null hypothesis is mu is less than or equal to 12, right? I keep getting that, not sure where that comes from. All right, so this is a what? This is a right tail test, right? So sample of 36 is taken with a sample mean of 12.5. So that means our z here, sample mean is 12.5. We have to subtract this mu from it, and then divide by standard deviation, which is 1 divided by square root of what? 36. There. That's our z. So we're going to get that z and put it over here, and then find the area to the right of it. On their z, right? This is z distribution. So that's how we're going to do it. Now what is that value? Again, we use normal CDF, right? And we do it. Oops. All right. So we're going to do normal CDF and find it. Now we could do it just on the original x bars, right? The reason we convert is because for t distribution, we don't have this luxury of working with the original x bars. So it's better to just convert to z. So we could do how much area is to the right of 12.5 under what? Under this distribution. Or, better even, we can convert this number to z and see how much area is to the right of that number. And that number, z, is the one I just wrote, right? 12.5 minus 12 divided by 1 over square root of 36. So with the normal distribution, as you see right here, we can find how much area is there, and the area looks like is about 0.0001, right? So that's the p-value, 0.0013. Okay, so let me make sure we understand this. So what I'm saying is that if you take the normal distribution CDF and then take the area to the right of 12.5, comma 10 to 99, and then the mean of 12 and a standard deviation of 1 divided by square root of 36, right? You would get 0.00134, which is the one I just have here. But if we could just go to normal CDF again, this time we're going to go to the right of that z. What is that z? Well, we could just put it here. The calculator calculates it. That z is 12.5 minus 12 divided by 1 divided by square root of 36, right? I don't know, 1, 2, 3, 1, 2, I guess I need have enough parentheses. So that's the z, that's the number, and we want to go from that number to what? To 10 to 99, right? So from here on, right? And this number right there is the number I just put there. I didn't put it, I let the calculator calculate what that is. And then comma what? Comma 0, comma 1, because the mean and standard deviation for z for this distribution is 0 and 1, right? And if I did everything correctly, I should get the same. Well, no, I have a extra somewhere. Oh yeah, I'm missing a parentheses somewhere. 1, 2. Oh yeah, I'm missing a 10 to 99. What am I missing? Oh, here. Oh, okay. 1. So that's the numerator divided by the denominator. Oh, I need a parentheses there. I need another one. So let me insert the parentheses. You don't have to do it this way. You could just calculate that number and put it there. But you get the same answer, right? That's what I mean. So this area is the same as that area, but we would rather do it this way because with t, we don't have this luxury to work with the original distribution. All right, find a p-value for a two-tailed test with a test stat of 2.14. Well, p-value for a two-tailed test, that means we have to go to basically 2.14 and negative 2.14 and then find these areas. But instead we can find the area of 1 and then multiply it by 2, right? So that's what it is here. So it's 2 times the area in the tail of test stat. Either this tail or this tail and then multiply it by 2, right? All right. So again, how do we do that with the calculator, right? We do 2 times normal CDF. The lower is 2.4, the upper is 10 to 99, mean and standard deviation, and then enter. All right, decision and conclusion, we said if the p-value is less than alpha, we reject. If it's greater than or equal to alpha, we fail to reject. Now remember, alpha is given. Alpha is the probability of making error 1. Now, how do we make the decision? Well, once we know whether we reject or fail to reject, then we're going to have to write in a statement. So this statement has to be about the claim. So if the claim is in the null hypothesis and you reject it, you say there is enough evidence to reject the claim, right? So if you reject, you always say there is enough evidence, right? If you reject, you always say there is enough evidence. Now, if the claim is in the null hypothesis, then you say there is enough evidence to reject the claim. But if the claim is in the alternative hypothesis and you reject this one, then you're actually supporting this. So what you say, if the claim is here and you reject the null hypothesis, you say there is enough evidence to support the claim. Now, what if you reject? Well, if you reject the null hypothesis, but if you fail to reject the null hypothesis, then you always say there is not enough evidence, right? There is not enough evidence. If the claim is here, you say there is not enough evidence to reject the claim. If the claim is here, you say there is not enough evidence to support the claim. So in your statement at the end, you have to have the claim. You have to say something about the claim. You cannot say there is not enough evidence to reject the null hypothesis, because people don't know what null hypothesis is. They know what the claim was. So you need to talk about the claim, and that's how you do it. There's only 4 different statements you can write. All right. So It's a Girl Genetics Labs claims their procedures improve the chances of a girl being born. The results for a test of a single population proportion are as follows. So here are the results. We got the null hypothesis, we got the alpha, and we got the p-value. Remember, if p is low, is smaller than alpha, you reject. In this case, we don't reject because this is bigger than that. This is 2.5%, this is 1%. So here we fail to reject the null hypothesis, right? And where is the claim here? This says that this labs claims that their procedure improved the chance of a girl being born. That means this is the claim. They say the probability of girl is greater than 50%. So that's the claim, right? Okay, so we failed to reject the null hypothesis, so we have to say there is not enough evidence to, should we say to reject the claim, or should we say to support the claim? Yes, you say to support the claim. So there is not enough evidence to support It's a Girl Genetics Labs claim. So you can write what it is, but that's what it says here, claim. So there is not enough evidence to support the claim. That's it. Here's another one. The p-value is almost 0 in this case. State the null and alternative hypothesis and interpret the p-value. It is believed that the mean height of high school students who play basketball on the school team is 73 inches with a standard deviation of 1.8. A random sample of 40 players is chosen. The sample mean was 71 inches and the sample standard deviation was 1.5 years. Do the data support the claim that the mean height is less than 73 inches? The p-value is almost 0, so we don't have to do it because the p-value is given, is almost 0. So since the p-value is almost 0, we reject, because the probability to get a number that big from the population, or from the sample, is almost 0. So we reject. Now, in order to write the conclusion, we have to what? We have to write the hypothesis. So let's do that. So we write the hypothesis and we know this is the claim, right? So the claim is that mu is less than 73. We are going to what? We have to reject that. So we say there is enough evidence to support the claim. We're not going to say to reject the claim because that's not the claim. The claim is here. So the p-value is almost zero, which means there is sufficient data, there is enough evidence to conclude that to support the claim, basically. Then you can write what the claim is, right? Now, at 5% level of significance, right? So in fact, even at 1% level of significance we still reject. So the level of significance alpha, normally if it's not given, it's 5%. And if it's given, it could be 1% or it could be 10%. Those are normal, those are commonly used numbers for alpha. All right, again, here is another example. It says the p-value is 0.026. State the null and alternative hypothesis and interpret the p-value. Again, this is the claim, so do we reject or do we fail to reject? Well, let's see. It says the p-value is 0.026 and alpha is 1%, so alpha is 0.01, but the p-value is 0.026, so that's bigger. So we fail to reject. So what do we say? There is not enough evidence to reject the claim, right? So the p-value is greater than 0.01, which means there is not sufficient data to reject that mean age of graduate students at university is at most 31 years. So now we're going to review again the three things we're going to do here and then do some examples, okay? So hypothesis test for a single population proportion. It's given like that. We talked about that already. So let's do some examples. So in a hypothesis test problem, you may see words such as the level of significance is 1%. The 1% is the preconceived or preset alpha. The statistician setting up the hypothesis test selects the value of alpha to use before collecting the sample data. If no level of significance is given, we use alpha, 5%. So when you calculate p-value and draw a picture, the p-value is the area in the left tail, the right tail, or split evenly between the two tails. We talked about that already. So we're going to have either a left tail, then the p-value would be this much area. And how do we know it's a left tail? Because the alternative hypothesis is what? Less than. Or we have a right tail, a two tail, which means alternative hypothesis is what? Not equal to. Then we get two tail. And then we take that number, we put it here, we calculate this area and multiply it by 2. And it could be a right tail. How do we know it's right tail? Because alternative hypothesis is greater than, right? And then we calculate this area, that's p-value. Okay, so let's do an example. June believes that 50% of first-time brides in the United States are younger than their grooms. She performs a hypothesis test to determine if the percentage is the same or different from 50%. June samples 100 first-time brides and 53 reply that they are younger than their grooms. For the hypothesis test, she uses 1% level of significance. Set up the hypothesis test. Okay, first of all, we say we have to write the hypotheses. So here, hypothesis is that because it says June believes that 50% of first-time brides in the United States are younger than their grooms. So this is something that we want to test. right? So she performs a hypothesis test to determine if the percentage is the same or different. So that's what we want to do. So June samples 100 first time. So we take a sample of 100, right? So that's our n. And then finds out that p prime is what? 53 divided by 100. That's our p prime, right? So takes a sample and it finds out that p prime is 53 over 100. So let's do that. So let's do it over here together, and then we. So here is p. We don't know. Oops. Well, let's do that. Come on. So that's p that we don't know. So we're going to take a sample of 100, and then p prime is going to be 53 over 100, right? So she performed a hypothesis to determine if the percentage is the same or different. So H null is that p equals to 0.5, and then the alternative is that is not. So what we have here is a two-tailed test. So what we have to do is we have to use normal distribution. We're going to use z. Now what is z? Z, or the test stat, is going to be p prime minus p that is hypothesized, right? This right here, divided by the standard deviation, which we're going to use p hypothesized and q hypothesized divided by n, that. And that number is going to be, well, let's use a calculator to do it. So that number is going to be, let's see, is going to be p prime, which is 53 divided by 100. Well, 53 divided by 100 is just 0.53, right? And minus, what is the p that is hypothesized is 0.5. So that's the numerator. We're going to divide that by square root of, again, 0.5, right? Because that's p that is hypothesized, times 0.5, which is 1 minus that, which is q sub 0, right? So which is 0.5 again. And so that's the numerator divided by n, which is 100. And that's it. So it's 0.6. So this number is 0.6. So this is 0.6. Now we have to take that number. Remember, this is a two-tailed test, right? So we have to put that 0.6, which is actually a big area. So that's 0.6, and this is negative 0.6. So how much area is there? Well, that's a lot of area, because that's a big piece of the graph. So we go to normal distribution, and we put 0.6, comma 10 to 99, comma 0, comma 1, and then multiply it by 2. That's 54%. So the p-value here, the p-value is 0.55, 55%. So that means it's not a rare event, right? Is pretty much within what we expected. We expected to get a number right here. And the probability to get a number, that far away from the mean is just about 55% chance, more than half. So that means we are not going to be able to reject the null hypothesis. So there's not enough evidence to reject that. So since if the claim is here, we can say there's not enough evidence to reject the claim if the claim is over here. There is not enough, but if the claim is here, right, then we say there's not enough evidence to support the claim. So it depends on which one of these somebody claims. We can say there is not enough evidence to support that the mean is different from 50%. All right, so let's look at the work now that we did together. And that's what the work is. Now again, we could use the original p prime distribution, or we just didn't use that, we use z, right? But they look kind of the same. That's what that is. All right, so now can we do this with the calculator? Yes, we could do it with the calculator. So let me show you how to do it with the calculator. Where was it? Right here. So to do it with the calculator, there is a region here, there is a feature that can do it for you. So we're going to go to Stat, Tests, and we are going to do 1 proportion z-test. 1 proportion z-test. So we're going to pick that one. Now notice that everything, all you have to do is put what? What is hypothesized? Well, hypothesized p is 0.5 in this problem, right? What is the x from the sample? Remember, she took sample of 100 and 53 of them said yes, or whatever, they satisfied the condition. So we put 53 and we put 100 for what? For n. And what kind of test do we have? Well, this is a two-tailed test, so we're going to pick that one, which is two-tailed test. This is left tail, this is right tail. And then calculate. There. So that's the 0.6 that we found, which is the t-stat, right? So t-stat was found here. And then p-value, which is 0.54, almost 0.5. And then this is p prime, or p hat, calculator calls it. Doesn't matter, it's 0.53. Now we could also do the same thing. This time instead of picking calculate, we can draw it. And you see it's going to draw what? Draw that for you. Make sure you have nothing under y equals to. Let me, well, my mode is off a little bit. So when you go to y equals to, there shouldn't be anything there. Otherwise, it doesn't have to do it again because I went out and did it. So let me do it again. So 1 proportion z-test, and I'm going to draw. So this is the p-value. Calculator doesn't draw rejection region. It calculates p-value for you. And the p-value is 0.55. So from there, calculator doesn't make decision for you. You have to use the idea that if p-value is less than alpha, you reject. All right. So one more I do for you. Jeffrey, as an 8-year-old, established a mean. So what I'm going to do, I'm going to do another video, B part, and do some more problems, okay? We got the concept under control. So now I'm going to do another video and do a bunch of problems. So let's say this is 57, slide 57. So I'm going to do another video, okay? So in the B video, I'm going to do much more, a few more examples to kind of get the concept under control, okay? So I see you in the next video. Take care.